Friends, today we will see part first of reagents in organic synthesis. There are five reagents for our study: sodium borohydride, lithium aluminum hydride, osmium tetroxide, selenium dioxide, 1,3-diethyl. Their uses in some of the specific reactions. So, reagents in organic synthesis, why these are required or what is the significance? Civilized world uses a great variety of organic compounds in everyday life: clothing, housing, feeding, transporting, defense, health, hygiene, many more. To meet these ever increasing demands, their production quantity is ever increasing. And organic synthesis is a challenging task where chemists deal with variety of reactions like dehydrogenation, oxidation, reduction, hydrolysis, esterification, nitration, sulfonation, alkylation, acylation, etc. And to carry out these reactions, large variety of reagents and to enhance the speed of the reaction, catalysts are needed. That means reagents and catalysts, these are the two important factors in the organic reactions. A reagent is a reactive chemical species that transforms the substrate to product. This is the definition of reagent. And a reagent need to be specific, cheap, easily available, and harmless for storage, transport, and handling. A catalyst is a chemical agent that accelerates the reaction. So, attempts are made constantly to develop new reagents and catalysts to improve organic synthesis. And we discuss here some of the reagents, and first reagent is sodium borohydride. Its structure is NaBH4, that is sodium borohydride. And this is prepared by reaction of boron or trimethoxyborane. This trimethoxyborane reacts with sodium hydride at 250 or a little more degrees, 250 degrees Celsius, and we get sodium borohydride. This sodium hydride required in the reaction can be prepared by reaction of sodium and hydrogen gas. So sodium borohydride is useful reducing agents. The reactions are carried out preferentially in protic solvents, and this protic solvents means solvents such as methanol, ethanol, water. In water, sodium borohydride hydrolyzes slowly releasing hydrogen gas, and hydrolysis can be fast at low pH. So reaction carried out in aqueous medium need to be fast. The first use of this sodium borohydride, that is, it reduces aldehydes to primary alcohol and ketones to secondary alcohol. Here, these are the two examples where benzaldehyde is reduced to benzyl alcohol. Here, see what change have been made. Only this is the structure of benzaldehyde. Only this carbonyl have been changed to CHOH. These two hydrogens are added to the carbonyl, one hydrogen to carbonyl carbon and one hydrogen to carbonyl oxygen, and we get benzyl alcohol. This is primary alcohol. Aldehydes are converted to primary alcohol, and here ketone are converted into secondary alcohol. Here double bond is replaced by single bond. Here one hydrogen and here one hydrogen. That means CHOH. This one is secondary. Then sodium borohydride is a mild and also more selective in its action. As it is mild, that means not so strong. So it is selective. In presence of other reducing group like nitro, ester, carboxyl, epoxide, nitrile, and double bond at room temperature or below it preferentially reduces carbonyl group. only. So, in presence of other groups, only carbonyl group is reduced to CHOH. Here, this ethyl gamma keto pentanone, it is not pentanone, it is pentanoate. So, ethyl gamma keto pentanoate in presence of sodium borohydride in methanol converts ethyl 4 hydroxy pentanoate. And what is the change? Change is only this C double bond O have been changed to CHOH. Only this change and remaining structure is as it is. And in every example you will see only C double bond O have been changed to CHOH. This is the only change. Here, here this aldehyde have been changed to primary alcohol. Here this ketone is changed to CHOH. Here this C double bond O CH to OH. Here this aldehyde and here this C chloral hydrate have been reduced to 2,2-trichloroethanol. So when other functional groups are present, it only reduces carbonyl to corresponding reduced groups. Metanitrobenzaldehyde, when this aldehyde have been changed to primary alcohol. Then second use of this sodium borohydride is reduction of carbonyl group to methylene group. Tosyl hydrazone are formed from carbonyl compounds by condensing with this tosyl hydrazone are formed from these carbonyl compounds by condensing with toluene sulfonyl hydrazine. This is toluene sulfonyl hydrazine, and this tosyl hydrazone form are reduced with the help of sodium borohydride, and we get alkanes or hydrocarbons. This is the useful reaction for preparation of ketosteroids. Third use, reduction of alkylation of amines. Reductive alkylation. That means reduction and alkylation. Both reactions are involved, and here aldehydes or ketones when treated with amines in presence of sodium borohydride causes reductive alkylation. Here this ketone, primary amine in presence of sodium borohydride. Reductive alkylation, that means here alkylation also takes place and reduction also takes place. Further reduction can occur, and here this will be the final product. Reduction of ester group, here ester are less reactive, so reduced slowly and inefficiently using excess of reagents and or elevated temperature, while carboxylic acids and amides are not at all reduced. Esters can be reduced, but excess sodium borohydride and elevated temperature, that means extra or more heating is required. So in harsh condition or in uh, drastic conditions, esters can be reduced with the help of sodium borohydride. But if there is a chance or there is a ketone group in the molecule, only ketone is reduced and not ester. That means selective reduction takes place when both the function groups are present. When both ester and aldehyde group are present, only aldehyde group is reduced. Then this is ester and this one is carbonyl aldehyde. Here only a change of aldehyde to primary alcohol takes place and this ester remains as it is. For more use, that is reduction of alpha beta unsaturated carbonyls, except in some cases it predominantly reduces only carbonyl group 1 2 reduction, that is cyclopent 2 ENEO, cyclopentanone, 2 cyclopentaenone, and cinnamaldehyde. So cyclopent 2 ENEONE reduction takes place by sodium borohydride in ethanol, and here cyclopentanol, 100% cyclopentanol is obtained, and this is the structure cyclopentanol. So what happened here? 1 2 reduction takes place. That means here this alpha beta unsaturated reduction of this alpha beta unsaturated carbonyl takes place. When cinnamaldehyde is reduced in presence of sodium borohydride in ethanol, we get this cinnamyl alcohol, 97%. Reduction of alkyl halide. Alkyl halide group is changed to alkyl group. Reduction can be carried out in presence of DMSO, that is dimethyl sulfoxide. So sodium borohydride reduces paranitrophenyl bromide. This CH2Br is converted into CH3. That means halogen is removed and it is replaced by hydrogen. Alkyl and remaining structures is as it was in the reactant. Reduction of C double bond N bond. C double bond N. The carbon nitrogen double bond of enamine, imine. These salts can be reduced with sodium borohydride, but it does not reduce nitride. So here, benzyl aniline in presence of sodium borohydride in methanol gives N-benzyl aniline. So here, this C double bond N is reduced, or reduction of the C double bond N takes place. Thank you.